On December 27, 2024, 3 volcanoes on Jupiter's moon Io erupted at the exact same time. Not near each other, hundreds of kilometers apart, the distance from New York to Philadelphia. NASA's infrared sensors recorded power outputs that maxed out the instruments, something that had never happened before, and it proved that everything scientists thought they knew about Io's interior was wrong. The 3 volcanic hotspots have designations now: P139, PV18, and an unnamed feature in Io's southern hemisphere. All 3 ignited within a single day of each other. Temperature readings showed they were burning at over 500 Kelvin, hot enough to vaporize lead. Combined, these eruptions produced 80 trillion watts of power. That's 6 times more energy than every power plant on Earth running simultaneously. But here's what made NASA scientists stop everything they were doing. All 3 eruptions shared nearly identical thermal signatures, as if something underground had triggered them all at once. Like 3 geysers in Yellowstone suddenly going off in perfect sync. Except these aren't geysers. They're volcanoes blasting molten rock into space. So what connects these volcanoes hundreds of kilometers apart? Is there a massive ocean of magma beneath Io's crust? Or something stranger? Io is one of 4 large moons orbiting Jupiter, the Galilean moons, discovered over 400 years ago. Europa is covered in ice floating on a liquid ocean. Ganymede is the largest moon in the solar system. Callisto's surface hasn't changed in billions of years. And then there's Io. Io orbits just 421,700 kilometers above Jupiter's cloud tops. That's just slightly farther than the distance from Earth to our moon. And unlike our moon, which is geologically dead, Io's entire surface gets replaced every 1,000 years. The fastest resurfacing rate of any world we know. Because Io is caught in a gravitational torture chamber. Jupiter's gravity at this distance is so intense that it stretches Io by 100 meters. That's the height of the Statue of Liberty, not pulling on water like Earth's ocean tides, but deforming solid rock. But Jupiter isn't working alone. 2 other massive moons, Europa and Ganymede, pull Io in the opposite direction. This gravitational tug-of-war forces Io into an oval orbit instead of a perfect circle. Every 42 hours, Io gets squeezed and released, like a stress ball in Jupiter's grip, forever. All that squeezing generates friction. Friction generates heat. Enough heat to power up to 400 active volcanoes scattered across Io's surface. Ever since NASA's Voyager 1 spotted volcanic eruptions on Io in 1979, scientists have been arguing about what's happening beneath the surface. 2 competing theories emerged. Theory 1. Io has a shallow global ocean of magma just beneath its crust. This ocean would fuel all the volcanoes at once, like a planet-wide lava lamp. Theory 2. Each volcano is powered by its own isolated pocket of magma. Hundreds of separate chambers scattered throughout Io's interior with no connection to each other. For 44 years, nobody could prove which model was correct. Until December 2023. NASA's Juno spacecraft made an extremely close flyby of Io, coming within 1,500 kilometers of the surface. Then it did it again in February 2024. During these passes, Juno used its radio transmitter to do something clever. As the spacecraft flew past Io, scientists on Earth measured tiny changes in the radio signal frequency. This is the Doppler effect, the same thing that makes an ambulance siren sound different as it drives past you. Those frequency shifts revealed how Io's gravity was tugging on the spacecraft, and gravity reveals mass distribution. If Io had a global magma ocean, the gravity field would be relatively smooth and uniform. If it had isolated pockets of magma, the gravity would be uneven, lumpy. On December 12, 2024, the results were published in the journal Nature. The verdict: no global magma ocean. Instead, Io's interior looks like Swiss cheese. Individual magma chambers, each feeding its own volcano or cluster of volcanoes. Separate pockets of molten rock as deep as 50 kilometers below the surface. Mystery solved. Except it wasn't. Because if every volcano has its own isolated magma chamber, how did 3 of them erupt in perfect synchronization on December 27th? This is where the December eruption changed everything. In 2024, NASA scientists compiled the first global heat flow map of Io using 30 years of spacecraft data. The map revealed that volcanic activity isn't random. It's concentrated in a band around Io's equator, within about 30 degrees north and south. The polar regions are quieter. Why? It comes down to how tidal squeezing works. When Jupiter's gravity deforms Io, the effect is strongest at the equator. Think about bending a paperclip. You bend it in the middle, not at the ends. Same principle here. The equatorial zones experienced the most intense stretching and heating. But the December 27th eruption revealed something nobody predicted. Temperature analysis from all 3 hotspots showed they ignited within 24 hours of each other, despite being separated by hundreds of kilometers. The only explanation is that these chambers aren't completely isolated. They're connected. It's like underground dominoes. Pressure builds up in one chamber. It reaches a threshold. That pressure wave propagates laterally through the network, triggering the next chamber, then the next. NASA's microwave radiometer, originally designed to study Jupiter's atmosphere, was also trained on Io during the recent flybys. Combined with infrared data, it detected something remarkable: warm magma that hasn't fully solidified yet, sitting beneath Io's cooled crust. Evidence of an active transport system moving molten rock around beneath the surface. So the real answer isn't magma ocean or isolated chambers. It's both. Individual volcanic engines connected by a network of channels we're only beginning to map. This underground network explains why Io's surface changes so violently. Take Loki Patera, the largest lava lake on Io. It's 200 kilometers across, big enough to swallow Los Angeles whole. In the center sits an island of cooled, solidified rock. Around it, a ring of molten lava constantly churns. Juno's 2024 images captured Loki Patera mid-overturn. Fresh magma rising to the surface. Cooled crust sinking back down. The entire lake convecting like a pot of boiling water. And then there are volcanoes that appear out of nowhere. Near Io's equator, scientists found a massive volcanic complex that didn't exist in 1997, when NASA's Galileo spacecraft last visited. The area was completely smooth. Now it's covered in lava flows spanning 180 kilometers in every direction. Michael Revine, who operates Juno's camera, put it perfectly. This large, complicated volcanic feature appears to have formed from nothing since 1997. An area the size of Connecticut completely resurfaced in less than 30 years. The colors tell the story. The reds are fresh lava, still cooling. The yellows are sulfur frost, volcanic snow that forms when erupted gas freezes at -130 degrees Celsius. The whites and blues are sulfur dioxide ice in the coldest shadowed craters. The greens are sulfur compounds chemically altered by Jupiter's radiation. Here's what makes this discovery bigger than just Io. Any moon with tidal heating could have similar connected magma systems. Europa, Enceladus, even Titan. The Doppler gravity technique that cracked Io's case is now being incorporated into Europa Clipper's mission plan when it arrives in 2030. If Europa's subsurface ocean has volcanic vents connected in networks like Io, it changes how we think about where life could exist. Because connected vent systems mean nutrients can spread, energy can distribute, chemistry can circulate across vast distances underwater. That's exactly the kind of environment where life might take hold. But here's the problem. After 44 years of questions, we finally have answers about Io. We know volcanoes are powered by individual chambers. We know some chambers connect in ways that allow synchronized eruptions. We've mapped subsurface temperatures for the first time. We've watched new volcanoes form in real time. And now there's no mission planned to go back. Juno is running out of fuel. The European Space Agency's JUICE mission arrives at Jupiter in 2031, but it's focused on Europa, Ganymede, and Callisto, the icy moons with subsurface oceans. NASA's Europa Clipper gets there in 2030, hunting for life beneath Europa's ice. Io? 0 dedicated missions. There's a proposal called the Io Volcano Observer. It would map the full extent of these magma networks. How widespread is the underground plumbing? Are chambers connected globally or just regionally? How fast can pressure waves travel through the system? But it hasn't been funded. So for now, Io's deepest secrets remain buried 50 kilometers beneath its crust, pulsing, churning, occasionally erupting in perfect synchronization, waiting. The December 27th eruption wasn't just the most powerful volcanic event ever recorded on Io. It was proof that Io isn't just a collection of volcanoes, it's a connected system, a moon-sized machine where gravity, magma, and time interact in ways we're only beginning to understand. And what we've learned about Io might be the key to finding life everywhere else.